Our first theorem, and this one continues to amaze me, was first a conjecture by the mathematician Pierre de Fermat. It was not, however, Fermat's last theorem, which was the famous one proved very recently in the 1990s. This one is instead called Fermat's little theorem. And what it states, most basically, is that if we choose two different numbers, usually called P and A, where P is a prime number, and A is co-prime, or relatively prime, to P. So, basically, P does not divide into A. Then we actually know we have a very important and interesting piece of information, and that is actually that this quantity here, A to the quantity P minus 1, is congruent to 1 modulo P. So I'll step you through some examples of what this really means. If we just for now take a constant prime number, and we'll go with perhaps 2, just to go with a more basic example. So if the prime is 2, then A can be basically any odd number, to make sure, of course, that it is relatively prime to 2. Because if it were any even number, then of course it would be divisible by 2. But we don't want that. We want it to be relatively prime. So the greatest common factor between P and A must be 1. So in this case, let's just give kind of the most basic example, which is if A equals 3. Well, in this case, A to the P minus 1 would be 3 to the 2 minus 1, which is really just 3. And what is this modulo P? Well, what is 3 modulo 2? Well, we actually know, as I described earlier, that's really just asking, is 3 even or odd? Well, we know it's odd, and it returns 1 upon division by 2. So that's just our most basic example. If we keep going, we get many more interesting things. So P equals 3 for the next few trials. Well then, let's choose an A which is relatively prime to 3. Well, in this case, we can choose 2. So, really what we're really doing is swapping our P and A from the first trial. And that's alright, we can do that. And 2 to the P minus 1, because we're going with this A and raising it to P minus 1, well that's 2 squared, which is 4. And of course 4 modulo 3, well that makes sense, that, you know, the remainder is just 1. Now let's keep going, let's try some other trials. If we start with 3, and then try 4. Because remember, we said A doesn't need to be prime, we need to make sure that it's relatively prime to this, you know, this P, this prime number. So in this case, 4 is A, so A to the P minus 1 is simply 4 to the second power, which is really 16. And this is interesting because, you see, 16 modulo 3, we can kind of work with it in our minds, and we know that 15 is the nearest multiple of 3. You know, the greatest multiple of 3 that's less than 16. And of course, 16 is just 1 greater than that. So the remainder is 1. Maybe I'll do 1 or 2 more trials, and then I'll show you an more extended table. But if we say 3, 7, I suppose we could say 3, 5 if we wanted to. But I think I like 7 in this case. So in this case we're getting, well, what is A to the P minus 1? That's 7 to the 3 minus 1, or just 7 squared, which is 49. And that modulo P, well, that modulo 3, what would that be in terms of the remainder? That would actually be equal to 1, because you see 48 is, of course, a multiple of 3. And if we moved on, I'm going to say 5 and 12. So clearly 5 does not divide into 12, and you know, 5 is our P, it's our prime number. And A to the P minus 1, well, let's calculate that. That would be 12 to the 5 minus 1, which is really 12 to the 4th power, which is 20,736. And that modulo P, if we mod that by 5, we can actually tell basically just by the ones digit that it is clearly 6, and you know, any integer ending in a 5 is, of course, a multiple of 5, so it's 1 greater, so the remainder is still 1. So really, all that I'm trying to demonstrate to you is a certain phenomenon. And I'm going to show you a more complete table right here. We've went over the case where the prime number is 2, and that's kind of the first set, or the first category. And then we did some ones where the prime is 3, and then I showed you one example of where the prime number is equal to 5. But I wanted to show you that this is actually, you can see for even more cases, that this theorem holds. And what this theorem, Fermat's little theorem, is actually describing is this final column here. And that's really describing what is this number, a to the p minus 1, modulo p. What is it congruent to modulo p? And in all of these cases, as long as p is a prime number and a is relatively prime to p, we know that this quantity must always be equal to 1. Now, first of all, isn't that amazing? Isn't that just... I'm at a loss for words. It's just so awesome and beautiful, elegant. You know, as is clear from this table, the formula works for a multitude of cases, and it's no wonder that Fermat originally conjectured that it works for all cases. And what originally amazes me, or what truly amazes me about this, is that P and A are selected so that they are unrelated to each other. If you think about it, they share no divisors. We're taking one prime number and some unrelated number. And this awesome pattern emerges. So to me, this is the act of kind of bringing order out of chaos. And it turns out, by August 1736, Euler indeed proved this theorem. And in fact, it was so fascinating to the mathematicians at the time, and that Euler felt the need to generalize it. And so in 1763, he completed the Euler-Toshin Theorem, actually, which is the next theorem on the list. And so, before I move on, I wanted to remember to show you something that is called the Euler-Totient Theorem, often denoted phi of n, basically. And it turns out to be a very important, very interesting function in number theory. And this is going to become very important in the next theorem I'm about to describe. And what it actually does is, for any given positive integer, n, so I guess I'll say that, n is a natural number, and it's going to return, I'm actually going to write this down, it returns all natural numbers basically from 1 to n. So it's basically traversing or going through all the positive integers less than n, which are coprime or relatively prime to n. And much of this information, by the way, comes from Wolfram Math World, a very good source, which I recommend you use. And so, also, this is called Euler's Totient Function. It's very important. The totient function at 0 is defined to be 1. It's equal to 1 by definition. And as it happens, there are several interesting properties of this function, and you can see them in a separate video here, although I might not have it up in a while, so please bear with me. But I'm going to work on that video eventually. Just for now, we'll go over some of the properties relevant to the Euler theorem, actually, or Euler's Totient Theorem. The main thing I'd like to say is that regarding this Totient Theorem, or Totient Function, I should say, you should know basically that the Totient Function at any prime number, and this is going to be important in a while, very soon actually. Well, think about it. How many natural numbers... Oh, and I should add, by the way, that 1 is defined to be coprime to all natural numbers. So, you start with 1, and that's actually possibly part of the reason why phi at 0 is defined to be 1. Because basically 1 is considered to be the lowest value of the Euler-Totient function. It's considered to be, you know, the reason for that is that it starts with 1, this function, and 1 is considered co-prime to all numbers. And so if we have phi of a prime number, then we're going to actually, what we're actually doing is going through each number from 1 to the prime number and seeing if they share any common divisors. But if you think about it, this prime number has to be co-prime to all of those numbers less than it, because it's prime. It's its prime factorization is just itself. As for the numbers less than n, if it's a prime number, this will by definition be p minus 1. That's what this quantity will be. So that's an important fact to bear in mind right as we go into this next theorem. And that is right here. Again, we're going to go through a few trials, and then we'll get to a more expanded table. We're actually going to start with a number n, a number a, which is again co-prime to n, and phi, we're going to study phi of n, and then take a to the phi of n and record what that is modulo n. So in this case it's asking a to the phi of n, where n equals 2, and a equals 3. Well, that's what we're basically doing, is taking 3 to the first, and 3 mod n is 3 mod 2, so that's also 1, because it's an odd number. In this next case, it's 2 and 5, so 5 to the first is 5, and 5 mod n, 5 mod 2, is also 1. And for this next one, we have a to the phi of n, so 7 to the 1, which is 7, and mod 2 is still 1. So you can see it's a similar phenomenon. So in this column, we're still getting 1s. We're still following similar patterns so far. We should keep going. That's what's so interesting about this theorem. You see, n no longer has to be prime, and yet we still have a formula. Let's check it out. So 5 squared, this is 25, and 7 squared, just for another example, that's 49. And what are these modulo 4? Well, it turns out they are still 1. 24 is the multiple of 4, so, 25 is 1 greater than that. 49, well, if you think about it, 48 is 4 times 12, so 48 is the multiple of 4. 49 is 1 greater than it. And now we get a couple cases where n equals 5, so, we can calculate that phi of 5 is equal to 4. It's kind of another case of where we're taking phi of a prime number. 5 is prime after all, and so is 3 for that matter. That's why we can quickly say phi of a prime number, well, that's just a prime number minus 1. Okay. And that works for all cases where n is a prime. Now, where n is not a prime, where n is 4, for instance, we could double check it. We should double check it. 4 to the 4, so we have 7 squared, 49, 13 squared, and these are indeed congruent to 1 modulo 6. So the pattern still holds. For any a we choose, as long as it's co-prime, we can use this formula, and we know that a to the phi of n is congruent to 1 modulo n. And that is Euler's theorem. So really, thank you very much for watching. If you like these topics, please consider subscribing to my channel. I appreciate it very much. But other than that, I'll see you later. One bonus theorem, and it may seem like I'm jumping a bit ahead, but there are a couple of later events I'd like to describe in this video. So a mathematician named Robert Daniel Carmichael, born 1879, got his PhD in 1911 from Princeton University, and this man became influential in his contributions to number theory. And more specifically, he devised the Carmichael Function, which is defined to be the lowest number, the lowest natural number, m, and I'll write this down. Usually it's denoted by a lowercase lambda, actually, so it's lambda of n, lowest number, let's say m, that solves the equation a to the lambda of n equals 1 mod n. So this is kind of building on Euler's theorem. And it might seem a bit cheap at first, but there's actually some very interesting consequences of this function, very interesting properties. And in fact, this special function is always a factor of the Euler Totient function. So this means actually that the Carmichael function is more efficient in solving the problem posed by Fermat, because it returns a value that is a factor of phi of n. And mathematicians say often that it is a stronger case of Euler's theorem for this reason. And now we can go back to this table and revise the last two rows, actually. Well, because the Carmichael function is stronger than the Euler Toshin function, we can actually replace phi of 8 in these two cells with lambda of 8, which changes this. This is why I have an asterisk. We change it, actually, to a 2. And what do we get? Well, instead of getting 8 to the 4th, this, kind of larger number, 625, we can actually kind of keep it simpler and say 5 squared is actually just 25. Okay. So instead of 625, we can actually say this is 25 right here. And 25 modulo 8 is still equal to 1, so this still holds. 6561, when that's, 6,000, that's kind of unnecessary. Instead, we can just say 81, because it's going to be 9 squared. So that's 81 in this cell by the Carmichael function, and that modulo 8 is still equal to 1. And I know this is quasi-empirical. I know I'm just showing you a few examples out of an infinite set, but I just want to give you a sense for what this really means. And you can take my word for it that this will work for all integral cases you choose, provided that n and a are co-prime to each other. And as for a proof of that, I will get back to you. I always hate saying that, but I haven't quite gotten there yet. These are just some very interesting theorems of number theory. Thank you very much for watching.